Hello, welcome to this class today. This is the lab class. So in this lab, you can see that we have covered some topics up to now. If you remember, in the last lab class, we have covered the topics for the linear algebra. Okay, so you can see that I have already uploaded uh, these scripts. So one is for the Gauss-Naive method, the other is the Gauss-Pivot method, and then is one script is for the tri-diagonal method. Later on, I will give you one assignment soon about this. And today we will cover the topic about the optimization. Okay, problem. So in the optimization, if you see the textbook, we started from the one-dimensional unconstrained optimization. And then today I want to show you how to write the script for the golden section search. So we will do the same example as I did here in this in the lecture, and then to solve this problem. Okay, to find the maximum of this function. Okay, so that we can get the table something like this. Okay, so I will go to the MATLAB, and remember that our function is 2 sine x minus x squared by 10. Okay, and given if we have been given this function 2 sine x minus x squared by 10, and within the interval of 0 to 4, we want to find the maximum value of this function. Okay, so by the golden section search method. So in this golden section search method, first of all, we calculate the value of d, that is the interval, which is the golden section search multiplied by the xl minus xu, and from there we calculate the x1 and x2 values. So we can repeat these steps, and then we can write the code about this. So for writing the code in MATLAB, so you will open the MATLAB, and in the command window, you will type edit to go into the editor window. Okay, and in editor window, you can write the code or script. Okay, so in this case, we can start from because we have already know what is the function we want, so we can start from xl l. Okay, I'm writing in L in capital L because later on I will be using x1 as well. X1 and xl look same, so therefore I will write xl as capital. Okay, so xl, the starting point is 0, and xu, this is 4. Okay, so these were the values. So for example, over here, xl is equal to 0, xu is equal to 4. And then I will define the function. So 2 sine x minus x squared by 10. So I will define the function. So the function is equal to at x. So it will show that the function will be in terms of x. 2 sine x, 2 times sine x, and minus x square divided by 10. So this is the function. This is the function. So if you want to define the function in this way, then you will put a gap between at x, and then you will write the right hand side of the function. Okay, so now for this, what I want to do is first, and the next thing is the next step, if you see that in this example, the next step is to find the value of d. So the value of d is equal to this golden ratio, square root of 5 minus 1 by 2. times xu minus xl. Okay, so we will find the value of d. So d is equal to this golden ratio. Golden ratio is sq rt, 5 square root of 5 minus 1 bracket close divided by 2. Okay, so this is the square root 5. So there is no need for this bracket. Square root of 5 minus 1 divided by 2. So this is the golden ratio multiplied by xu minus xl. Okay, and this is the value of d. Value of d, we have calculated it. Next is we will calculate the value of x1 and x2. So x1 is equal to d, sorry, x1 is equal to xl plus d, and xu is equal to xu minus d. Okay, so we will calculate x1 is equal to xl plus d, and x2 is equal to xu minus d. So we have written it, x1 and x2. And the next step is what? Next step is, okay, so once we have calculated it, then what we can do is we can check, okay, that the two conditions. Okay, we can check the two conditions. So for example, what are these two conditions? So once we check it, we have to evaluate the values of fx2 and fx1. Okay, so we can evaluate it. So which is this over here? So we can evaluate the values of fx1. So fx1. That means once we calculate these values of x1 and x2, we have to calculate the values of this function fx1, which is equal to for this function, and then its argument is x1. Okay, and then next we calculate fx2. This is the equal to the function with its argument of fx2. Okay, so fx1 and fx2 we have calculated. So now we will check it with the help of if statement. So if fx1 is if fx1 is less than fx2, then x1 is equal to x2, and or xu will be equal to xu. Okay, and else, that means else if fx1 is greater than or fx2, there will be no such situation fx1 is equal to fx2 because of the property of this golden section search. So we don't need to check it. So else sorry, this is xl. Okay, sorry, we need to check xl. Then xl will be equal to x2. Okay, else xl will be equal to xl and xu is equal to x1. So these are the conditions, and then end. So this is the situation, because this situation, for example, over here is due to these two rules. Okay, it is happening with respect to this figure 13.4. Okay. So for example, if fx1 is greater than fx2, that is, remember that if I'm just recalling it, although I have explained when I was giving the lecture that x1 will be x2 will be on the left of x1. Okay, because x2 is by subtracting d from xu, and and we are subtracting like 61% of that distance. And then similarly, x1 will be towards on the right of x2. So the xl, x2, x1, and xu, this will be the situation. So in this case, if fx1 is greater than fx2, then the domain of x to the left of xu from xl to x2 can be eliminated because it does not contain the maximum. So for this case, x2 becomes the new xl. Okay, x2 becomes the new xl. So xl will be equal to x2. So that's why what I have put. And xu will be as before, that is x2, xu. So this is what I have put. xl will become x2 and xu will be equal to x2, xu. And it says that the assignment to xu might be unnecessary, but anyway, we can put it. And then in the second case, otherwise xl will be equal to xl, and then xu will be equal to x1. So in the second case, so let's go to over here. It's in the second case, it says that when it is opposite, then x1 becomes the new xu. So xu is equal to x1. Xu is equal to x1. So this is how it goes. Okay, so this is just one iteration. So for repeating it, I think we have to repeat it several times. Okay, so for repeating it, we have to repeat it several times. So we need to repeat it. For the next iteration, we have to, because now we have new xl and xu values. So therefore, we need to calculate the new x1 and x2 values and the new d values. So therefore, we will need to input a loop over here. So that loop will be, maybe in this case, I can use for loop. Okay, for I is equal to 1 to 10. Okay, I want to repeat it, say 10. Later on, we can change it. Okay, so maybe you can, if you want more repetitions, we can change it from maybe 20 or like that. So for I is equal to 1 to 10, I will repeat it. And then I will repeat it until here, end. Okay. So this will be the end for this full for loop. So from here to here, it will be repeated. This thing will be repeated 10 times. Okay, but now somehow we have to provide the output of the results as well. So we have to print the results as well. So first of all, we need to print these column headings, table headings. So as in this case, yeah, this is the table. We have to print these table headings as well. So for this, we can put the fprintf statement over here. So I have already copied it. So I will just paste it over here. So this will be the, yes. So, okay, so this will be the table fprintf. So I want these headings: iteration, xl. So I can put it like xl, and then fxl, x2, fx2, and then x1, fx1, and then xu, fxu, then v, and then xopt. What is xopt? Yeah, this is something extra which is not shown in the book, but will be useful. Xopt is that I take the average of x1 and x2, because for the if we take the more and more iterations, so the value, the optimum value of the x will be somewhere between x1 and x2. So as the interval between x1 and x2 becomes narrow and narrow, so we come close and close to the results. And then f opt is the value of the function with that optimum value. So this for we have put these variables. So now in this case, inside of the for loop, so we are now calculating d, and we are calculating x1, x2, and then from x1 and x2, then we can calculate the x optimum. Okay, x optimum, which is equal to x1 plus x2 divided by 2. Okay, and then I can also calculate the f optimum, which is simply equal to f of x optimum. Okay, that means simply take this value of optimum and then calculate the value of this function. So this is f optimum. And now we have to, I have to print it as well. So I have to print these values as well. So for example, up to now we have calculated these values. And now I have to print these values before this if statement. Okay. So for what value I want to print? I want to print these values. So whatever values I want to print, I place it in a row matrix. Okay. So I want to print I. I will come from this for statement. That is the iteration, first iteration and then when it will be run for the second one, it will give the value of I as 2. Then I want to print is XL. Then I want to print is then I want to print is FXL. FXL. So FXL is yeah, we can print FXL as well. So for this, I think I need to define it over here. XL is come from here, and FX1, FX2 is here, maybe FXL over here. So FXL, so it is equal to F of XL and then FXU is equal to F of XU. Okay, so I need also these values. So these values I want to print. So I want to print it into this matrix XL. Then F X L. Then I will print X2, F X2. And then I will print X1. Then I will F X1. And then XU and then FXU, okay, and then D, and then X optimum, and then F optimum, yeah, and that's all. So these are the values I want to print over here. So, and then I will place it with this one, and then I will place the fprintf command. That means fprintf. So, so first of all is the %10d. That means this is for the iteration, and then 10.5f, and then so I should have as many number of arguments of this %10f and %10d as the number of members in over here. So here we have 1, and then 8, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 members. And here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So hopefully it is correct. And then at the end, for backslash n, and then I have put this z, which is this matrix over here to tell this fprintf command that what value I want to print. So I think with this, hopefully the code is completed, and then I can save this code, save as Golden Search Lab. Okay, Golden Search Lab. Okay, I saved it with this name, and then I can run it by clicking this run command. And then I have seen that it has run without any error. So let me hide this place, and it has run it. Okay. So here I am getting these values. Here I am getting these values, but here I think I see some problem with these values over here, because if I compare my results with these values, so I get 001.5279, 1.7647. So what results I am getting is 001. Yeah, it's okay. It's 1.4. Optimum value is 1.41859, but it is not decreasing. So there is some issue with this, some issue with the code. Okay, so some issue with the code. So the code has run correctly, but I'm not getting the results which I was expecting. X optimum value. Yeah, X optimum value. Yeah, here I think it seems to be correct. Maybe this X optimum value, the formula is not correct over here. Yeah, I think the maybe I need to see what is the formula which I put for the X optimum. It is X1 plus X2 over 2. The formula is correct. The formula is correct. It is 2, 2, 2, but here FXL, maybe I think I made some mistake. So what is SQRT? Square root of 5 minus 1 over, that is correct. So once you make a mistake, then I think it is also a part to check the mistake. So it is 2 sine x minus x squared by 10. Whether it is correct. 2 sine x minus x squared by 10. Okay. Yeah, this is correct. And then for I is equal to 1 to 10 square root of 5 xu minus xl. And then I calculated x1 is equal to xl plus d, xu is equal to xu minus d, x optimum is equal to x1 plus x2. That is x1 is here, x2 is here, and then f optimum is equal to f optimum. And then fxl. In fact, I think maybe it is correct, but I think maybe what I can do is I can make it simplify. Okay, make it simple. I don't need to actually calculate this function fxl, fx2 like that. I can just simply calculate the x opt and then up to here. Okay, this may be causing some confusion. Okay, over here. And now what I can do is I can just modify it a little bit. Okay, so XL, X1, X2, I calculate it, then I calculate the X opt, X1, X2, and then XL, I want f of XL. So in this, instead of f of XL as the variable name, I just put it in the function form, f of XL. It is x2, then f of x2, x1. So this is x1. Then this will be f of x1. Okay. XU. Then this will be f of XU. Okay. And this is D. Then x optimum, f optimum. And f optimum will be here, f x optimum, f of x optimum. Okay, and yes, this is the one. So if fx1 and here now I think we have to calculate f of x1 and f of x2 is less than 1, then that's it. So maybe now I can calculate it. So I will clear it, and then I run this code, Golden Search Lab. So, okay, so f optimum is now, again, there is some problem with the results. Where is this? So the results are showing that the values of the functions are something like what approaching about 1.7755. Okay, 1.7755. These much values are approaching, but the results which I am getting is something like which is approaching, which is not converging over here. Therefore, there is some issue with this. XL is equal to X2, XL is equal to XL. Here, no, I think there's an issue with that. Yeah, this needs to be calculated. Okay. So on the other hand, I think I can, if I can show you over here, this is the one. This is another code which I calculated, which I developed before separately. So if I apply this one, in here I have this function x square over 10 minus 2 sine x. So it is actually an opposite of that function. So maybe if I want to apply this over here, I will change it to minus. Okay, so it will be 2 sine x minus x square by 10. And here I have these values over here, just in the separate way. So if I apply this one, and then I run this code, and now it is giving me these values. These are the same values which I am getting it. Strange. Okay, so if I apply it with this, clear in CLC, and yeah. And now I apply. So here now I am getting these answers, okay? So now the answers are approaching to minus 1.77573. Okay, so what I have, what has been done over here is this is the for the negative of that function. So negative of that function. So in this case, we are finding the maximum of that value. So what we have found is over here is the maximum of that value is minus 1.77573. So in this way, then the code will work. So here I have used the function as 2 sine x minus x squared by 10. Okay, so 2 sine x minus x squared by 10, the value of the maximum of this function was found to be like this. It was CLC and then this one. So we have found this value minus 3.0577. So if I take some more iterations over here, like this 20, okay, and then I apply again. So this one, and then, so you can see that the value is approaching minus 3.11315. So which means that this is going to give us some value, okay? So 3.99 and then 3.113, 3.11. So the value is approaching over here. Okay. So it is 2 sine x minus x squared by 10. Okay, so do you have any questions about this? Hello?
No questions?
No, no questions.
Okay. So 2 sine x minus x squared by 10. Okay, so with this thing in mind, okay, so this is how then you can write the script for this golden search, golden section search, okay? Golden section search. So in this case, then you have another method, which is the parabolic interpolation. So you can, in a similar way, you can also write the script for this parabolic interpolation as well. So this will be rather easier in this case. Maybe there is no need to write the if statement because we are not going to specifically check for that if fx1 is greater than fx2 or like that. So simply we can repeat it. So there will be no need to write an if statement, just a for loop or while a loop with some limiting the stopping error can be applied. Okay, so there is also other approach for finding the maximum or minimum of a function. Okay, so for example, if we want to find the minimum of a function in MATLAB, so now I close these scripts and clear this screen. Here, see. For this, we use another a function for finding the minimum of a function. We use an fx. We use a MATLAB function, which is called f min b and d. F min b and d. So we use this function. So suppose if we have the same function as uh, 2 sine x minus x squared by 10, okay, and we want to apply this built-in MATLAB function. So how we can apply it? So its syntax is its syntax is like that. So this function can generate two values. So x min and f val is equal to f min b and d, f min b and d function itself, and then we need to provide the xl and x1 and x2 values. Okay, x1 and x2 values, and the uh, x1 and x2 values. So suppose if we want to, if we have the function fx is equal to 2 sine x minus x squared by 10, if we want to find the minimum between 0 and 4, so what we can do is we can say that xl is equal to x1 is equal to 0, okay, and x2 is equal to 4, and then we can define the function as f is equal to at x 2 times sine of x minus x squared by 10. This is the function. So suppose if we have this function x squared by 10. So, and now if I want to find the minimum of this function, so that is 2 sine x minus x squared by 10, the minimum value of, so for this I want to find that value of x and the corresponding value of the function. So then I can apply it like this. X min will be a variable in which the value of x for the minimum value of function will be stored, and fval will be the function, will be the variable for which the value of the function will be stored, and then that is equal to f min b and d. That is the function name, and its argument is the function itself. So function name is just represented by f over here. We have stored it in the function f, and its first value is x1, which is 0, and the second value is x2, which is 4. So, and then I will close it. And when I press enter, so it will give us the x minimum value is equal to 3.999 minus 3.1135. So that means that if we want to find the minimum of this function, then that minimum will occur at 3.999 and minus 3.1135, which was the same value which we got for our script. So if I run our script, so for example, Golden Search Lab, if I open that script, Golden Search Lab, this which we just developed, and then I run this script, Golden Search Lab. So we see that we got the same answers. Okay, so therefore we are finding the minimum of this value by this function. Okay, so if we want to find the maximum of this function, then we need to just modify this script a little bit according to these two rules. Okay, so we have to look closely at these two rules. So for example, these two rules, where Where is this? Yeah, these two rules. Okay, and then we want to modify these rules. Okay. Alternatively, if we want to say uh, want to find the alternatively, if we want to find this f min b and d like this, and then if we want to find the maximum from this function, then we have to take the negative of this value of this function, and then we want to we will just apply it. Okay, so let's do it. So for example, these were the minimum values. So here, let me clear everything. Clear CLC. Okay, and now let me see, define the x1 is equal to 0 first, x2 is equal to 4, and the value of the function is this one. Okay, and then I apply this mean, yeah, this one, and then this gives me the minimum values. But now let's say if I want the maximum value between 0 and 4. So what I will do is I will take xl is equal to 0, x1 is equal to 0, x2 is equal to 4, and I will define the function like this. Okay, here I will need to do is I will take the negative of that function, negative value of that function. So it is equal to minus this, and then plus this, x squared by 10 minus 2 sine x. And then I will apply this x min. Now in this case it will be x, not x min, it will be x max, and then max value. Okay, this is the max value. Okay, so now I can enter it, and now in this case you can see that the maximum of this function occurs at 1.4275. Okay, and the that maximum value is minus 1.7757. Right, so I think maybe we can also see it in the by the plot of this function. So for example, if we want to plot it, yeah, let me see what is this function. So function is this. Okay, so if I want to plot this function, so for example, yeah, if I want to plot this function, so I can take x is equal to linspace. Okay, linspace 0, 4. Okay, that means I take the x values between 0 to 4, and then I take I have defined the function fx, function f. Okay, so function f, in this case I just put this 2 sine x minus x squared by 10. So I have this function. So now I have defined x is equal to this, and this is equal to sine x minus x over 10. And no, I need to just modify it. X, I have to 2 times sine x. This is a scalar. Then this is a vector, and then is here I will need to take dot star to divide it by 10, and then this is the value of the function. And now I will plot x comma f. Okay, and then I will get this plot. So here you can see that, so this function is from 0 to 4. The maximum of this function is here. The maximum of this function is here. So it is between 1.5 and 2. So it is 1.7. Okay, and the value is 1.77, something like this. The minimum of this function, which was calculated to be the minimum of this function is calculated to be 3.999. So which is actually true, and because it is almost equal to 4, because we are calculating it numerically. So basically the minimum is at the end. The minimum of this function is at the end. Okay. So for this type of function, the minimum is at the end. The maximum is somewhere in the middle. Okay. So this is how this has been calculated. Plot xf is equal to this. Okay. So is it clear how we can use this value of? Do you have any questions? Hello?
Yes, yes.
Yes. I'm asking, do you have any question?
No,
No?
it's understandable.
Okay. So then we have seen that how this fmin BND function works. So therefore, if I just apply it again, x1 is equal to 0, x2 is equal to 4, and then I take the this function, and then I apply this value, then I can get this. Okay, these values. So this function is a kind of like a black box. What I mean is that we have, although we have found the end result, that is the value of x, for which we have found the maximum of that and the maximum value of that function, but how it was calculated, this is not clear. So if we want to see the details of this, we can use a function which is called as the optim set. Okay, optim set for details. Okay, optim set for details. So how we can use the optim set? So optim set will be, let me show it to you. So it will be the options. So we will store this store the options for that in this by using this optim set function. So optim set is the function. Options is a variable. Optim set is a function. And say we want to display the details. Okay, so we will use a string which is called as the display, and we will also use a string which is called as the iterations. So iter, iterations, and then we will close it. Okay, so these are the options for this function. And then if I want to now show the value, find the value of this, x max is equal to this, and just apply it without any variable. And in addition, I add another parameter with that, options. Options is this a variable which I have defined over here. Okay, and then I hit enter it, and then in this case I will get the details of the calculations. So this will give us some details. So it will say that it will start from these initial values of this. Let's initialize these values because it is using from these previous initial values. So let's initialize these values from as 0 and 1. So let me do it again. So f min this one, and then let's take this, instead of x1 x2 I will take the initial value 0 and 4, and then I save it as 2 values. Okay, or just like 1 value is also fine. So 0 and 4, and now I will put it. So here I will get this result. So you can see that the values for this function initial values are 1.52 and minus 1.76, the initial values. And then initially this process has applied the golden search method, and then it has switched to the parabolic search method. Okay, so which means that the two of the methods which we have learned in the text are used. So golden and parabolic. That means this function is a very smart function. It changes from one method to another method to get the results quickly. So this is how it shows. That means it started from the golden search method for the 2 iterations, and then for the next 4 or 5 iterations, it uses the parabolic search method. So the inbuilt function is much in this case. In this case, it is much smart than our search results which we have obtained. So in the end, it is giving us this value of 1.4275, which is the same as before. Okay, so any questions?
So we can use this function to check, yes?
Yes, so you can check your answer by using this fmin BLD, right? So suppose you write a script for the golden search method, and then you find the answer, and then you can check your answer with this function. Okay, so the next is the, so this was, these were the discussion about the one-dimensional, okay? So one-dimensional method. If we want to find the, for the multi-dimensional, so multi-dimensional optimization, multi-dimensional optimization, okay? So for this multi-dimensional optimization, you can use another MATLAB function, which is called as the fmin. That is, you can another MATLAB function which is called as the fmin search. Okay, you can use fmin search function. So it's so it is for the multi-dimensional. That means for more than one variables. So suppose if we have an equation, let me show you that equation. Okay, can you see this? If I have this equation, f of x1 and x2 is equal to 2 plus x1 minus x2, and 2 minus x1 square plus 2 x1 x2 and plus x2 square. Can you see it?
Yes.
Yes. So this equation is a multi-dimensional equation because it has two independent variables, x1 and x2. Okay. So let me write this function first. Okay. So yeah, actually I can just show only one function at one time. So let me write this function over here. So if I write this function as something like in this form, so I can write this function like something like this. So I can write this function as this. So f is equal to at x. Sorry, f is equal to at x. So the function starts from 2. So I will write 2, then plus x1 plus x1 1. So here you can see that for these two x1 and x2 variables, I will use this notation x and then in the bracket 1. Okay, so that will show that this is x1 and minus x2 minus x in the bracket 2 and then plus 2 times x 1 square x1 and then square plus 2 times x1 times x2 plus x2 square. Okay, so this is how the function is written. So you can see that 2x1 minus x2 plus 2x1 square plus 2x1 x2 plus x2 square. Okay, okay, so this function has been written over here. And now if we want to find the a minimum of this function, okay, if we want to minimize this function, so I will use this f minimum search. So for this, I need two outputs. One is the value of x for which the function will be minimum, and then the value of the function as well. So value of the function. Okay. So then I will put, then I will store it into this matrix variable, and then f min search. So this is the function name, and then the name of the function for which we want to find the variable. So this is f is the multi-dimensional variable, and then for this function, I need to provide two guesses. Okay, that means what is the guess for x1, and the other is what is the guess for x2. Okay, so that means for x1, I can say that maybe minus 0.5, and for x2 I can say that maybe 0.5. Okay, and then I provide these two values over here, and then I hit enter, and then it will give me the answers. Okay, it will give me the answers. That means the value of the function will be 0.75. That will be the minimum value of this function at these two values of x1. So x1 is equal to -1 and x2 is equal to 1.5. Okay, so -1 and 1.5. So that will be the minimum value of this function, 0.75. So this is how we can find the minimum of this function for the multi-dimensional variables. So for the one, this function can also be used for one-dimensional variables as well, but for multi-dimensional we have to use this function. And in this one-dimensional variable we have used this f min b and d. But for one-dimensional variables, so for one-dimensional functions we have to use this f min b and d. This may be more efficient than f min search. The difference between f min search and the f min b and d is that f min b and d uses the golden search and the parabolic methods, whereas the f min search actually using the just random search method. Okay, so this is the difference between these two values. Okay, so yes, so do you have any question about this f min search? Okay, so Hello? Hello?
I think we don't have any questions.
Okay. So this is how we will use the fmin search. So here we can see that, remember that these fmin search and fmin b and d both are providing you the minimum values of the function. If you want to find the maximum value of the function between the given intervals, then you have to take the negative of that function and then apply it. Then that will give you the maximum value of that function. So by default, it is providing you the minimum values. Okay, so this you should remember. All right, so then I think we covered the linear programming with the simplex method in the last lecture. So the linear programming by the simplex method can be also done in the script form in the MATLAB. However, we can also do it very conveniently in the Microsoft Excel. Okay, so let me see where were we in this constrained optimization. So in this case, today we have covered the MATLAB application for the golden search method, right? MATLAB application for the golden search method. And then we also, you can, I did not do it, but in a similar way, you can apply the parabolic interpolation. And then there is this Newton's method, which is same as the Newton-Raphson method, which we did for the root finding. So I don't have to repeat it, okay, over here, Newton-Raphson method. And then for the multidimensional, we did one example for this in the using the Excel, okay. And then we have also applied the fmin search method for this, okay, in the MATLAB. Then for the constrained optimization, where is this constrained optimization chapter? Yeah, constrained optimization chapter. In the lecture time, we have learned about the linear programming. That is how to develop the standard form of the linear programming problem. And then how to do it with the graphical method. And then in the last lecture, we did the simplex method, okay, simplex method. So, and then one thing which is remaining is the application of this simplex method in Excel, okay. And application of the simplex method in Excel, and then the non-linear programming as well, that is also in the Excel, okay, this is remaining. So yeah, so we can do the linear programming in the Excel as well. So how we can do it? So see, let's do this same example over here. So for example, what was this example in the, which was this, the problem, the situation of the problem was this, okay, the same problem. Here, yeah, so this was the problem. So we have to maximize 150x plus 175x2. So let me go to the Excel over here. So maximize, okay, maximize, and by 150, and then yeah, 150, and then 175. We have to maximize it by maximizing, but what x values. So we have x1 values is just take 1 and 1, okay. So we have to maximize it, this one, that is 150 times this plus 175 times this value. So I have to maximize this value. Okay, we have to maximize this value. And then the constraints are what are the constraints? What are the constraints? So let me go back to this. So the constraints are 7x1 plus 11x2 is equal to 77. So 7, 11, 77. Okay. So the constraints are 7, 11 is less than or equal to 77. Okay. 7 and 11 is less than or equal. Maybe I will put it like this. Okay, and then should be less than, and then the second constraint is where is this? Second constraint is 10 and 8, 10, 8, 80. So 10, 8, 80. So 10, 8. I think you are familiar with this example. So is less than or equal to 80. And then the other constraint is other constraint is what? Yes, x1 is less than or equal to 9, x2 is less than or equal to 6. X1 is less than or equal to 9, x2 is less than or equal to 6. So 9 and 6. So 9 and 6. So you can put, this is x1, this is x2. So, and then I can put the formula for that. 7 times x1 plus 11 times x2. Okay, and then 10 times x1 plus 8 times x2. So it is 18. So let me, for this clarification, I can put it like this is this is the value of x1. This is the value of x2. So we have to find the solution here. Okay, we have to find the solution here. So we can use the solver method over here. So this is the solver data, which is available in the data, and then we go and go to the solver. So a solver is asking us what? Asking us set the objective. So what is the objective over here? So the objective over here is this. Okay, this objective. This objective have to be maximized. So I will select the max button over here. Okay, and by changing cells, so we want to change is these two cells. I want to change it, and subject to the constraints. So for the constraints, I need to add the constraints. So the first constraint is this value. Okay, should be less than or equal to 77. Okay, and then I will add this constraint. Another constraint is which one? Yeah, sorry, this value should be less than or equal to 80. This is another constraint. And one more constraint is that the value of x1 should be less than or equal to, because if you see that over here, the value of x1 should be less than or equal to 9, x2 should be less than or equal to 6. So these are the two more constraints. So the value of x1 should be less than or equal to 9. I have added this constraint, and then the value of x2 should be less than or equal to 6. And then I will add it. And then I click OK. So I have added these constraints. So these 4 constraints have been added. And the another constraint is that make the unconstrained variables negative, non-negative, that means positive. So that means all the values of x1 and x2 will be considered as non-negative. So we don't have to add them as separately over here. So once I have selected it, then maybe it will be better for you, for us to select the appropriate solving method. So GRG nonlinear is used for the nonlinear programmings, okay? So, but for especially for the linear programming, we can use the simplex LP, okay? So we can use this method over here, and then I hit the solve button. So by hitting the solve button, it says that the solver found a solution. All constraints and optimality conditions are satisfied. So here you can see that we have got the solution for x1 value is 4.889 and x2 value is 3.889. And the maximize objective function is 1413. And by doing this, these 2 constraints have also been fully satisfied, but the other 2 constraints have not been fully satisfied. Maybe I could show it over here, but because yeah, we can see that it was 4.88, so its limit was 9. So it was 3.88, its limit was 6. Okay, 9 and 6. So this is the solution. Okay, so and with this solution, you can also generate the report as well. Answer. So maybe 2 of these reports, answer and sensitivity reports, you can generate. Okay, and then you can click OK. So once you will generate these reports, then you will see that there are 2 more sheets that will open. One will be the answer report, so it will show the answers. So for example, when we maximized it, then the answer was 1413. The values of the variables were this, and which were the non-binding, which were the binding. So, and then what was the slack in those cases. Okay, for x1 the slack was 4.11, x2 the slack was 2.11. And in the sensitivity report, we will also get some very useful information. Okay, so this sensitivity report, I leave it for tomorrow lecture for some time. I will explain it. So this sensitivity report simply will show that which of the variables is more sensitive. That means in this case, we can get a value something like for this shadow price over here. So this is 10.18 and 7.87. So this shadow price actually will show that the higher the shadow price, that will show that higher is that variable for the sensitivity. So that means if we will change this variable, that is for the first variable was for the this was for the supply. Okay, yeah, for the supply, for the 77, that was for the supply. So if this supply can be increased to say from 77 to 78, then what will be the increase in the profit? So for like that. So this sensitivity will show like this. So for example, if the constraint is increased from 77 to 78, then the increase in the price or increase in this objective value will be by 10. On the other hand, for the if we change from 80 to 81, the increase in the objective value will be 7.87. In this case, this 77, that variable is more sensitive. So in this case, we can see the sensitivity report. So yeah, tomorrow, I think in the lecture, I will also explain this sensitivity report a little bit, and then we will also do the optimization with Excel for the non-linear method, which is similar to this linear method, because we will be using this same solver add-in. All right, so that's all for today. Do you have any questions?